Avigad from Carnegie Mellon, and he will be giving a talk on a verified algebraic representation of Cairo program execution.
Good, thank you very much. So I think you're all looking at my slides, and I hope you all hear me. So okay, good. So far, so good. Okay, so I'm going to describe a verification project that I did with colleagues at a company called Starkware, which is based in Israel. And I'm going to try to run through a lot of material in the short time I have. So I'm going to tell you a little bit about blockchain and smart contracts and cryptographic proof protocols. I'm going to give you an overview of what we did. And then for the specifics, I'll tell you a little bit more about the machine model and some polynomial constraints, and then give you a statement of the main theorem. So let's see. So the acronym STARK stands for Scalable Transparent Argument of Knowledge, which is a description of and the name of a particular cryptographic proof protocol. The company develops blockchain solutions based on that proof protocol, and it provides methods of carrying out things like exchanges and auctions and so on blockchain efficiently. And I'll try to give you a sense of how that works. And the project was to use the Lean Proof Assistant to verify some of their methods and code. So if you're a newcomer to blockchain like me, it's best to think of it in functional terms. It's just, blockchain is just a magic ledger in the sky, and it grows, and nothing is ever deleted. But not everybody can write anything. I mean, users have control over resources and can transfer them, transfer control over what gets written to the ledger. And of course, the application is things like, banking and financial transactions, without government or institutional involvement. And there's a lot that goes on under the hood to make that work. But from the point of view of this talk, you can think of it just as a black box. It's just a magic ledger in the sky. And the second stage of magic are smart contracts. So smart contracts are just computer programs that you can put, on the chain, on the ledger, that get executed automatically when some condition is met. So for example, if you and I want to do a currency exchange, I can put my currency, in escrow on blockchain and put a smart contract on blockchain that says that if you transfer your currency to me, then, mine gets transferred to you. And once the smart contract is put there, it can't be revoked. And so you do the transfer, and and my currency gets transferred back to you. And once again, this is the kind of thing that usually, we rely on governments or, or banks or lawyers in courts or credit card companies to oversee. And this, gives you a way of doing things like that without any kind of institutional control. And again, there's magic under the hood, of executing things on blockchain. But from the point of view of this talk, we can take that as a black box as well. The problem that Starkware addresses is that running code on blockchain is both expensive and slow. So the reason it's expensive, so resource-wise, is that everybody maintaining the blockchain has to execute the code, to verify the integrity. Okay, so that's sort of a lot of people running the same code. And then moreover, it's slow. So I'm told that, for example, if you consider the number of transactions that a company like Visa will perform in a second, that this just, vastly dwarfs the kind of bandwidth you can get on blockchain. So the way around it is to use cryptographic proof protocols. So these things, have been around since the 1990s. And roughly, this is how they work. So, there's some kind of relation, R of X, Y, and there's some public data, A. And I want to convince you that I have in hand a B such that R holds of A comma B. So in particular, such a B exists, and moreover, I know of one. So one solution is for me just to show you B, and then you check that R holds of A, B, and we're done. And the problem is that if B is long and the relation is hard to check, this is inefficient. So cryptographic proof protocols are designed to do exactly this. But do it more efficiently. And the trade-off is that it's probabilistic. So, I send you some information, and then you, randomly query me. And if I can respond appropriately, then you have high confidence that, in fact, I have the value B that I claimed. Okay, so this is how cryptographic proof protocol works. So how do you translate this to running code on blockchain efficiently?
Well, we specify a model of computation, some kind of register machine and, execution semantics, and that's fixed. And in fact, the model we're going to use has read-only memory. So the idea is we're going to arrange things so that a successful run of a program um, um, is supposed to convince you that that a claim is true. And the prover, I'm obligated to sort of put things in memory so that so that I can guarantee that the program runs to completion. Right. So what we do is, publicly we agree as to a partial assignment to memory. So typically, the program that's going to be run, the input, and then the claimed output. And we agree on the starting state of the processor and the final state. Right. And what I want to do is I want to convince you that there's a full assignment to memory that extends the partial one, and an execution trace, for that memory from the start state to the final state, that runs successfully. I don't have to show you what goes into the memory. You might not even care, right? I just have to convince you that there's some way of extending the partial assignment that we agreed on to make the program run. And that's what Starks can do efficiently. Right, so that's what I'm going to explain. So I've told you about blockchain and smart contracts and the proof protocols. So now let me describe the verification project. Right. So one interesting verification project would be to formalize cryptographic claims about Starks. And that's not what we did. So here we'll just take that as a black box. We'll assume that Starks work as they're supposed to. The company was interested in two verification jobs for Lean. The first was verifying the reduction from the execution semantics to Starks. And then they're also interested in verifying then particular programs. So for example, programs that run auctions or exchanges or things like that, to verify them against their specifications. So the second one is ongoing, but what I'm reporting on here in this talk is the successful completion of the first one. Okay. And the formalization you can find online. In fact, it's set up with Gitpod. You can even run it in the cloud without too much difficulty, hopefully. So you can see all the details. Okay. Okay. So here's how Starks work. So we fix a large prime number p, and we let f sub p be the finite field of integers modulo p. Okay. And what the Stark protocol allows you to do is, well, it allows me to convince you that I have a table of field elements, so elements of the field, satisfying a bunch of polynomial constraints. And these are kind of parametric. The details, the specifics aren't really all that important. But the idea is roughly, so for example, we might have a polynomial P1 that mentions any number of rows, right? And and remember, the data is arranged in a table. And what I want to convince you is that I can make the claim that that polynomial holds of every row, offset from every row in the table, or it can be every second row, or every fourth row, or every 16th row, or something like that. Okay, but so we have a bunch of parametric polynomials, and the Stark protocol gives me an efficient way to convince you that those polynomials hold, that I have a table of field elements satisfying those polynomials. So remember, my goal is to convince you that there's a full assignment to memory extending a partial one that we agree on, and an execution trace from the start state to the final state. So that's the nail, right? That's that's what we want to accomplish. The protocol will convince you that I have a table of data satisfying some polynomial constraints. So that's the hammer, right? So, to bridge the gap, what you want to do is you want to encode statements about execution traces of programs in terms of tables of data satisfying polynomial constraints. So that's the algebraic intermediate representation. AIR stands for algebraic intermediate representation. Okay, but of course, if this is going to be convincing to you, I should also prove to you that the encoding is correct, that it does what it says. And the company has a detailed white paper, where it describes the machine model and the polynomials, and it gives a fairly detailed sketch that the polynomials do what they're supposed to. But the proof is only a sketch. Not all the details are worked out fully, and they're very fiddly, and they're very delicate. And so what you really want on top of that is a verified proof. And so that's what we have done in Lean. Okay, so let me tell you about the machine model. So it's a very simple register machine. So you have a central processing unit, a CPU that has 3 registers. One is used as a program counter, and the 2 are just sort of pointers into memory. The assembly language is very simple. You can basically assert that things are equal. So you can say that, for example, the contents of memory location X are equal to the contents of memory location Y plus 3. And there are various ways you can address memory, with directly or offsets from values and so on. But there's a jump, there's a conditional jump, there's a call, and there's a return. And an interesting feature of the model is that the elements are always, the memory values are values in the finite field. Okay, so the operations you can refer to on memory elements are plus and times. So there's no notion of ordering. They're not integers. They're not bits. They're just elements of the field. Okay. And so, there's a white paper specification of the CPU. And if you go online, you can find the formal specification in Lean. And, it's the file isn't very big. It's about 100 lines. And, at the very end, you have a next state relation. So that says that given an assignment to memory, and given a state S, it says that T, is a possible successor state to S according to the model. And it is a relation, so it's important to keep in mind that there may be no next state, so an assertion can fail, whereas the program can just crash, essentially. Or if instructions are not well formed, there may be undefined behavior, so there may be multiple next states. And so, instructions, an instruction consists of 15 1-bit flags and 3 16-bit vectors. And there's really nothing, kind of exceptional about it again. So the state is just kind of the 3 registers, the program counter, allocation pointer, and frame pointer. And, there are things like this, that, if the flags are set in a certain way, if the flags are set for a call, for example, for a function call, then the specification is the next value of the frame pointer is supposed to be the current value of the allocation pointer plus 2, and so on. Right? So there's about 100 lines of, specifications like this. Okay. All right, so that's the machine model. And so remember, the polynomial constraints are supposed to guarantee the existence of a valid trace consistent with the publicly, agreed on assignment to memory. And so, there are polynomial constraints that deal with saying that things are valid instructions and interpreting, the components of the instruction as bits, bit flags and so on. Part of the verification requires knowing that the field elements, in fact, are casts of integers in various ranges. So, for example, an instruction is coded as an integer from 0 to 2 to the 63rd. It's a 63-bit value. There are constraints that guarantee that the memory assignment is valid and extends the public one. And then there are constraints that ensure that each successive step follows the machine semantics. And in the formalization, the constraints are found in various places. So in each file, locally the constraints that are used are there. Then there's one file that collects them all together. And then we have the same constraints in a slightly different format that were generated from the Starkware code that is actually used to generate the Stark certificates. Right. So it's important to know that, when we verify the execution traces, they're against the actual polynomials that are used in, to generate the certificates. Right. So the code that generates those certificates has an internal representation. We output them as in Lean format as well. And users, the certificates make this public, right? So users can verify that, in fact, these are the polynomials that, are used for the certificate. And so that's the starting point for the proof. So again, the point of the proof in Lean is to verify that, if there exists a table of values satisfying these polynomials, then there exists an execution trace of the machine. Okay, and just to give you a flavor, I mean, this is it looks auto-generated. This is kind of what the code looks like. So you can find a just a file full of things like this. So this is three polynomial constraints, right? So C is the table of columns and so on. Okay. So good. So I've told you about blockchain and smart contracts and the proof protocols. I've told you the verification tasks and described, there's an execution semantics and polynomials. So now let me tell you about the statement of the theorem that we proved. So as a first cut, the theorem says something like this. So given a partial assignment to memory that we publicly agree on, and a start state and a final state, and a table of data satisfying the polynomial constraints, right? This data is enough to guarantee that there exists a total assignment to memory extending the partial one that we agreed on, and a valid execution trace from the start state to the final state. There's a complication, though, which is that it's not possible to do this efficiently as I've described with the polynomial constraints. So the problem is that, when you write down the constraints, there are various places where you want to refer to field elements, and you want to say that, to specify the next step relation, you want to say that, position AI, some field element AI, at that position in memory, there is the value vi. Okay. And so in the table, you have a list of pairs with assertions like these. Okay. But then globally, for that entire list of pairs, you want constraints that guarantee that this is a consistent memory assignment, right? So we don't contradict ourselves about what values are found in which locations, because remember, we're assuming that this is read-only memory. Okay. And then, moreover, we need to guarantee that that the claims we've made are consistent with the partial assignment to memory that we publicly agree to. And the problem is that these are global constraints about a long list of values. And with polynomials, what polynomials are good at is kind of relating, for example, one row of the table to the next. Right? So it's not good for doing global things. A similar problem arises that we also need to, in various places, guarantee that a field element is the cast of an integer in a certain range. And there's no easy way to do that with polynomials. Right. So the solution is to use cryptographic trick inside the global cryptographic trick. And I can't go into all the details, but roughly speaking, the way the protocol works is that first the prover commits to certain columns of data. Then a cryptographic hash is generated, right? A random challenge. And then the prover responds with 2 more columns of data. And the theorem that we prove is actually the theorem that, with high probability, the fact that the data satisfies the constraints implies the desired conclusion. Okay. So again, here's the real statement of the main theorem. Right? So given a partial assignment to memory that we agree on, the start state, final state, and a table of data, okay, there exist small sets, B1, B2, B3, such that given field elements x1, x2, x3, so think of these as being generated randomly by a cryptographic hash, and 2 more columns of data. Then if the x's are not in the corresponding b's, and all the data satisfies the polynomial constraints, with respect to the memory and the x's and so on, then there exists, then the conclusion holds that there exists a total assignment to memory extending the partial one and a valid execution trace from the start state to the final state. And here it is, right? So here's the formal theorem. It says just that. Here's a finite field of characteristic at least 2 to the 63rd. Here's the public data that we all agree on. Here's the table of values that I, the prover, have. So given that, there are 3 bad sets that are not so big, such that given 2 more columns of data, such that everything satisfies all the polynomial constraints, and the randomly generated hash elements, are not inside the bad sets, then there exists an assignment to memory generalizing, extending the partial one, and there exists an execution state from the start state, an execution sequence from the start state to the finish state, such that each successive state follows according to the machine semantics. Okay. So just to finish up, there's a lot of related work. We know of nothing quite exactly, quite like what we've done. But of course, there's a lot of work in, formal processor semantics and verification of cryptographic protocols. I mean, we heard about that in the last talk. The Pinocchio project is something nearby, reasonably close to what we've done. And as I said, the next step of the project is to then verify specific Cairo programs with respect to this semantics. And that, which I haven't discussed here, but that looks more like conventional program verification with some twists, given the quirks of the model. And finally, the final remark is that blockchain and smart contracts, I think, are a very good target for verification. So I think really this domain may be the killer app for formal verification. Because on the one hand, smart contracts aren't all that complicated, so they're not terribly hard to verify. But I've been told that that billions of dollars are lost each year because of of errors, but badly designed smart contracts. So there's money riding on them. So people really do care about the results. So it's a case where people care about the results and the verification isn't too hard. So I think it's really a good market for the domain. So that's it. Thank you very much.
So let's all thank Jeremy for this really cool talk. So do we have any questions yet in the Q&A? Not yet, but how about in Philly?
Not yet. Oh, yeah, there's one. Give me a second.
So,
Hello.
yes.
So thanks for a great presentation and for explaining Starks and in a quite accessible manner. I always suffer with those things. So my question is about the application domain a little bit. I know that this was not the topic of the talk, but you mentioned that the idea is to verify smart contracts. And I'm curious about what are these Starks are going to be intended, where are they going to be placed? Is this intended to be a system in which it's a layer one, in which all the network distributes these crypto games, so these Starks, or it's intended to be a roll-up solution in which transactions are compressed into some sort of a cryptographic hash, which is embedded in a layer one, which is on another blockchain, and in which case, which is the target? It's supposed to be a multi-blockchain application. It's supposed to be a specific blockchain, and why?
Yeah. So thank you. So yeah, I mean, you were kind to thank me for the simple explanation of blockchain and smart contracts. My knowledge doesn't run any deeper than that. So so that's why it came out so naive and simple. So really, I'm out of my domain here. So my understanding is that this is what you would call layer two, right? So ultimately, the certificates are published on blockchain, and I think the certificates are verified with Solidity. So that would be like the layer one. And this is kind of a model to then let you run code more efficiently. So I think in the terminology, this counts as a layer two approach. And the nice thing is that you can go to the company, you can find a lot of information about their web pages. So they do run an exchange, a StarkX exchange. So there is an exchange that runs and is transferring transferring lots of money between currencies. So that's one application that the company is using internally. But there are also platforms that other users can use. So I think this is what you would call rollups and so on. So I think it's both. I think they're trying to market this as kind of solutions that others can use for auctions and gaming and really anything that they might want to do on blockchain.
There's a follow-up question about the same.
Okay, thanks for the answers. So you are mentioning then, so basically layer two, that means that you mentioned EVM, so I imagine that this language in which you're describing the circuits is powerful enough to encode everything that is being encoded in EVM. And I know this is perhaps not the topic, but it's actually something that they are looking into actually prove or something like that.
Yeah. So first of all, it's a Turing complete language. I mean, there are loops. Well, in kind of a funny sense, there are operations over a field and so on. But there are loops and recursion. And again, I encourage you. You can go to the Starkware web pages. The name of the programming language is Cairo. There's a low-level assembly language which I described, and then there's a slightly higher level kind of functional programming language. You can have memories and structures, and you can call functions recursively and so on. And so there's the Cairo programs are compiled down to the assembly language ones. And yeah, I mean, so they are very concerned the language is still under development, but it is already in use. But they are concerned to design the language to make it really an expressive language. It has to be both expressive so the language is written, you're still very close to the machine. You're very sensitive to, how many instructions. They're always optimizing their programs to try to shave off, a few steps and so on. Because again, even with the compression, the computation is expensive. But the language is designed to really, kind of be close to the metal, but at the same time be expressive enough to let you do what you want to do.
Thanks. Alon, we don't have questions local here in Philly currently. Do you have more online?
You don't see any. Sometimes it takes a while for them to appear. Let's see. So Cairo is a really simple architecture. If you had a more complicated architecture, how do you think that affects the proof or not? Just curious.
Yeah. So when I came on board, the engineers had already designed the language and the algebraic encoding. It's really very clever. So it is. The processor was designed to be simple enough so that the constraints are very complicated to unpack the bits and so on. So I think it would be hard to get much more. It would. So I think they were looking for balance. They're trying to make it just complicated enough to do what they wanted to do.
Right. Okay. So any more questions, either in the audience or?
No, not here. So.
Okay. So let's thank
you.
Speaker again.